that the shades is displaying is narrow. It's only displaying black and white basically. Okay? Well, we have a wide dynamic range where it's displaying a lot of shades of gray. Not noise. This is something.
No, I mean mixes, black and white. Narrow.
Narrow. Black.
Mixes.
Mixes.
Mixed, like black and white.
Narrow.
Is it like a house per unit or something, or
A house per unit? Nah. I wouldn't compare it to that. I wouldn't compare it to the decibels that are being. Not like a Hounsfield unit, because that's based on the matter, right? The Hounsfield unit is based on the how X-ray photons display. You know, this isn't like that, because we can change this. You know, it's gonna either change. So basically, what compression is gonna do is gonna make your blacks blacker and your whites whiter. Okay, it's gonna take away the grays. Okay. It's going to make your blacks blacker and your whites whiter. Somewhat like how harmonics does that, right? Mm-hmm. But to a lesser degree, because harmonics does it in a completely different way. But it works similarly, where it's going to make your look at my brightness right here. Now look at it, it's super bright, right? Mm-hmm. Okay, and look at everything that's dark. It's going to make it. It was gray, but now it's going to make it very dark. Okay, meaning our range of colors that is displaying is going to be narrow. Okay, we're only going to see, so we can see black, gray, and white with a narrow display, right? Black, gray, and white. That's all we see. With a wide dynamic range, we're going to see black, off black, light gray, dark gray, medium gray, off white, white.
So it's more contrast.
More contrast right here.
Yeah.
Definitely.
Narrow.
So for a liver, would you rather have like an A or a B?
B on a liver. We want to have wide dynamic range, so we want to be able to differentiate those gray shades within that actual liver itself. I want to be able to see the different if there's a mass, because the mass can look similar to the normal parenchyma of the actual liver. I need to be able to differentiate that. If I have everything kind of mashed up, then I won't be able to see it.
what would you use the narrow
I'll use narrow dynamic range when I'm looking at blood vessels. If I need, because you know how sometimes that haziness will be in the middle of a vein, and I can't get it out of there, I'll use dynamic range to get rid of that haziness or those low level echoes. Okay, but you gotta be careful with this compression, right? Because it's gonna change all the echoes just the same. It can take away important information.
Right.
Right. So you gotta be careful with it. Same thing. You gotta be careful with the harmonics when you hit it. Right? Because you can take away. You can have sludge in the gallbladder. You bring down your dynamic range, and now it's a clean gallbladder.
How do you adjust it on the machine?
Yeah. Where's it on the machine?
Gray maps.
Gray map?
Gray maps. Gray maps is right here. But this machine also has compression as well. So you can do it two different ways on it. And I'm going to show you how it looks in 1 second. Let's get through it real quick. So the effects it has on the image is that it changes the grayscale characteristics of an image. You guys already wrote that because that was the initial slide. Okay? And it is adjustable. It is adjustable. Okay? So amplification, compensation, and compression are all adjustable. Alright? Again, two kinds. One cannot be changed and is integrated into the system. That's the one that it arranges so the system it's in the system parameters, basically. It's in the system parameters. Then we have another user control compression that modifies grayscale mapping. Grayscale mapping, our gray maps right here. It modifies that. Okay. Let's see what I have on right here. Hopefully you guys can see in the back. It's too much. But again, I'm gonna use my thyroid. You wanna come up and do what you can.
That's good.
Can you see that?
Yes. It's too much narrow.
Right there. So guys, I'm gonna use my gray maps. It's set to 3 right now. So I'm gonna bring it down to 1.
No.
See now, I made it for a more black and white image. You guys see that? And now I'm going to increase it to 5. Now I have a more grays on my compression. Okay? It's real subtle to the naked eye, right? It's real subtle to the naked eye, but that's what's happening. So more grays right there, more black and white image right there. Okay. Also, I'm gonna adjust the other compression right here, right there. Now I have a really black and white image, right? My compression down to 47. I think that's the min. It goes, yeah, 46 is the minimum, right there. I think it goes to 100 or 78. Now I have more. It's more gray. You guys see that?
Mm-hmm.
I have more gray right there. I bring my dynamic range down. Now it's more black and white. We're good? Okay. So on this machine, 2 ways to control that would be our gray maps. Gray maps does it at a bigger scale. The compression on here does it more incrementally. You got me? Kind of. So gray maps would do it like in big jumps, where the compression. Thank you, man. The compression actually do it in smaller, where you can actually see the smaller changes that are happening. Okay. The AGC. That is
Penetration.
the AGC is. It's kind of that's on the what machine is that? That the AGC, it actually, as you move around, it means automatic gain compensation. It's automatically gonna adjust for gain everywhere you move your transducer. So you don't have to go and press iScan. You don't have to go and adjust your gain so much.
Yeah.
Really?
So does it have something to do with the grains as well, like make them?
It changes. It's going to change your whole image though. As you move your transducer, it does it automatically. It's going to change your whole image. It does the compression, the amplification, does all of that. It works just like if I use iScan. Just like if I use iScan there, it's going to optimize my image. If I use iScan here, it's going to do the same thing. With AGC on, it's going to do it automatically no matter what. It's supposed to. That's the purpose of it. To amplify, it's automatic gain compensation.
So you just turn it on, it's not something you adjust.
So as you're moving, you don't have to hit iScan all the time. Okay? It's like having iScan on every single time you move the transducer. I don't use it that much, obviously, because I have like AGC. I'm like, oh, that, yeah. I don't use it that often, but that's what it does. That's what it does. Okay. Okay. Any question on compression, guys? 2 kinds of compression, right? One adjusts to the system parameters. The other one is adjusted for our eyes, so we can see. We can only see 20 shades of gray. Okay. Again, compression is in decimals. Compression is in decimals. A little bit more about compression. Log compression, remember that's a synonym. What's the other synonym?
Dynamic range.
Dynamic range. What's our synonym for compensation? Myra?
T.
No, yeah, no. Yeah, that's gonna be in Dewey's head. He ain't never gonna forget. All right, guys. So log compression is clinically important for the technology because we're able to see the differences in the weak reflections. Okay. It makes good contrast. We'll be able to, if we increase the dynamic range, we're going to make a more black and white image on this machine. If we decrease, that may change based on the machine, guys. I'm not going to say it's like that on every single machine. Okay? So as you adjust it, you can see the small differences in weak signals, and it's going to make a wide range of strong reflectors bright white. Right? Correct? So when I turn it up, it's going to make my blacks look a little darker, and my whites be really bright. So I'm going to cover demodulation, guys, before we get out of here. I came in a couple of minutes late, I'm sorry. But demodulation, guys, it changes the form of the electrical signals within the receiver so that it's more suitable for display on the monitor. Demodulation, this is the one right here, guys. We don't mess with it. It's automatically happening. It's automatically happening with or without our consent. We don't get to adjust it. It's automatically, the system is automatically doing this, okay? So it's changing the form of electrical signals within the receiver so that it's more suitable for display on the monitor. All right? The effect it has on the image, it has no visible effect on the image. This has everything to do with the signals being received, okay? It has everything to do with the signals being received. There's no visible effect on the image. If I have a question, which receiver operation has no visible effect on the image? The modulation, compensation, reject, compression. The modulation. Okay. It also has no synonyms. Okay? It has no synonyms as well. Alright? It is not adjustable by the sonographer. We can't adjust it. Again, it's just making our signals more suitable for display on the monitor. Alright? Also a two-part process. Compression, demodulation, back-to-back, receiver operations, two-part process. Okay? This is the picture out of the book. Sorry guys, I cut it off a little bit. I don't know when I took my picture, I guess it didn't apply to that part. So the first part is called rectification. Okay? You guys that are in physics, X-ray physics especially, you know all about rectification. That's going to convert all our negative voltages into positive voltages. It's basically, rectification is eliminating all negative voltages. So we know how our beam travels like that, right? It's effectively going to flip all of our negative voltages to the positive side. Okay? Don't ask me why it does that, how it does that. I'm telling you what it is. These are one of those things that we just gotta accept. All right? Please don't. I don't know the minutia. I'm not gonna lie to you, but I know what the modulation is. Okay? So rectification is gonna convert all of our negative signals into positive signals. I'm sorry, all of our negative voltages into positive voltages. Basically, putting them on the positive side of our spectral analysis. Okay? Changing the form of electrical signal by eliminating and correcting for negative voltages. Okay? Then we have what's called smoothing. The second part is called smoothing or enveloping. Okay? I know what this one does. Okay? That places a smooth line around the bumps and evens them out. Okay? See, it's going down. We don't have a smooth line around the bumps. This has everything to do with it being consistent, right? And everything to do with the signal being consistent, that it's increasing at the same rate and it's decreasing at the same rate. It's not increasing, decreasing at different times. Okay? Same thing like in X-ray, like in CT. It works the same way. Dr. Black teaching this right now. Okay? So, first part, rectification. Negative voltages turn into positive voltages. Second part is called enveloping or smoothing. Okay? And that's going to place a smooth line around the bumps and even them out for a much smoother, a much more consistent signal. Okay? You got a question, dude?
No, I was just thinking about the second one, because over there in my country, if you want your work smoother, you gotta get them the envelope. So
you're gonna remember that. You're gonna remember that. All right, guys. I'm gonna pick it up next class on Monday on reject. Real quick, any questions, guys? Can you hit that like that? Any questions on the beamformer and the fourth operation of the receiver that we talked about today? Any questions on those? Guys, I want to see great grades on the test.